Okay, so let's have a go at this question. So the first question is asking about L and what type of logic gate must be there. Well, you need a logic gate that will output when a logic 0 is going in. Okay, so there we go. So logic 0. So you want something that will allow it through. So the gate I would always go with probably would be the NOR. However, you could choose an OR gate, you could choose an XOR, or you could choose an XNOR, because obviously you want something that's going to give you a 1 out when you've got the zeros going in. Question 2, astable. On the data sheet you have an equation for the high time TH, the low time TL, and the frequency, which basically puts TH and TL together, but the examiner's done that for you, so it's quite easy. Basically F equals 1.44, it's all on the data sheet, over 10 or 10k, isn't it, plus 2 times 10k, so 10 times 10 to the 3 plus 2 times 10 times 10 to the 3, all multiplied by C. Yeah, microfarad. If you put that into your calculator, press equals, you'll get around about 10 hertz, 10.2 hertz. Okay. Okay, so mark to space ratio, again on the data sheet you have this. To be honest, there's a couple of ways you could do this. You can clearly see that it charges through 2 lots of resistors, or 20k, and it'll discharge through 10k. So I can actually just look at that and realise it's a 20 to 10 or 2 to 1 mark to space ratio. However, on the data sheet there is an equation for that as well. Okay, so it's R1 plus R2, R1 plus R2 divided by where are we? Divided by R2. Okay. Okay, it's the same thing, 2 to 1. Right, next, okay, so we have a number generator. The key thing here, just to realise, actually, because it resets on 6, okay, so 6 isn't allowed, so basically it resets here. Okay, so nothing should happen in these boxes, essentially, because it's reset. Okay, so it resets there, essentially, that's the idea. Okay. Okay, so P. I mean, what you could obviously go back round to 0, 0, 0 as well, by the way, but I'm just dotting those out. Okay, so P is an AND gate with B and A as the inputs. Well, B and A give me a 1 there. Obviously, it would have given me a 1 down there, but we don't need to worry about that one. The rest are zeros. X is looking at the OR with P and C. Those are 2 inputs, so I'm looking at P and C, and I'm going down and putting a 1. So I should get those 3 as 1s. Y is looking at the XOR. There's Y there. It's looking at the XOR of B and XOR'd with A. So I know an XOR gate's called a difference gate. So when they're different, B and A, I should get a 1. So when they're different, which are those 3 cases there. Hopefully I've got that one right as well. And then Z is looking at the NOT of A. So that's easy. Okay, so that is that one there. 5 marks for that one. Just take your time with it. Realise though, it's that thing there, it does reset as well. So if you do carry on, you'd lose 1 mark. So don't worry too much, but obviously do what you can. Okay, so this is a bog standard D-type flip-flop. I'm just going to hopefully you can see where the data and the clock lines are on this. There's the pen, the pen's out. If you can't see it, the data does go up there. I'll just draw it in actually, just so you can see where it does change. There's my data line there. clock obviously is that one. So just be thinking, how does a D-type flip-flop work? Well, a D-type flip-flop works, D moves through to Q on the rising edge of the clock. The only difference is with this D-type flip-flop is you've got a set and a reset here. So if you put logic 1 into the set, it will instantaneously set. If you put logic 1 into the reset, it will instantaneously reset. It says Q is initially a logic 0. So Q is initially a logic 0. Here we go. The first time it sets, I'm going to go up to a 1. Okay. It's going to stay there until the first clock pulse. There are my 3 clock pulses. What's the statement? Q copies D on the rising edge of the clock. So the first clock pulse, what is D? Yes, it's 0. On the next clock pulse, which is here, what is D? Yes, it's 1. On the third clock pulse, what is D? Yes, it's 1. But then the only other thing is it will reset because you're telling it to reset there. Okay, so that's the idea of that one. Q copies D on the rising edge of the clock pulse. Obviously, you don't have to wait for the clock pulses to set and reset because the SR flip-flop does not need a clock pulse. Okay. Okay, so what's this one? A sequence generator. This is the one that the examiner always likes. Lots of easy marks. So for 5 marks, let's see if we can work out the Boolean expression for DC. There's DC, you can just see it there. So it's an OR gate and it's connected to B. So it's going to be B ORed with the other bit, which looks to me to be it looks to me to be C and not A. C and not A. Okay, I'll just check that against my one. Yep. DB then is this one here. It's an OR gate again. So we'll trace this line first. It's going to be not B, or it looks like to be where are we? It looks like it's going to be not A, not C. So not A, not C. Okay. Again, I'll check that against mine. Yep. And then the last one is an XOR gate. It's B XORed with A, isn't it? B XORed with A. Then we just need to go down here. So next state, DC. I need to look at the current state. So DC, again, this is my logic for DC. Look, you can see it. It's saying anywhere where B is a 1, I would get a 1 out, while B is a 0 in this particular one. Look, there's B. It's a 0 there, isn't it? Yeah. So anywhere where B is a 1, I would get a 1 out. I can't seem to delete that bit. Okay. Or anywhere where C is a 1 and A is a 0. Well, look, C is actually a 1 and A is actually a 0 there. So I know that it's going to be a 1 there. You can see that idea. DB, it's looking at not B, or straight away that precedes, is that the word? Yeah, basically trumps, let's use that word. Basically means that's going to definitely give you a 1 out. And DA is an XOR gate, looking at B and A as the inputs. Well, 2 zeros into an XOR gate will give me a 0 out. Then we write this diagonally down. I'm just going to write the next ones in until it repeats. Feel free to pause and try this yourself, but I'm just going to write them in. So I'm just going to look at the data sheet, the mark scheme, to write it until where it repeats. Okay. Okay, that is where it repeats. So I'm going to change my colour pen. So you keep going till it repeats. 1 0 0 happens up there, so that's where it repeats. Then I write down my other unused states, which I haven't used. So the first number is 0 0 0. Have I used 0 0 1 next? No, so I'll write that next. Have I used 0 1 0 next? No, so I'll write that. And then have I used, yeah, and then last number I've not used is all the ones, 1 1 1. Okay. And then what you do is you apply the logic here. So DC, again, we're looking up here. We're looking at B or C and not A. So, well, anywhere where B is a 1, I might as well put those in, because I know B is a 1, those two. So that these two, I'm looking at C and not A. C and not A. There's 0 there, and there's a 0 there. Okay. DB, I'm looking for not B first, so I might as well stick 1s there. And now I'm going to look at not A and not C. Not A and not C happens there. It doesn't happen there. And then DA, I'm looking at the XOR of B and A. There we go. It's 4 marks. You can get the marks. It will take 4 minutes at least to do this one. That's absolutely fine if it does take that long. But you've got 9 marks in total there, guys. You should be able to do that. Sequence generators. Okay. Okay. So please have a look at the mark scheme for this one, but it's basically going to be 4 like that. Yeah, you have to actually write what's in there, guys. I'm just going to be lazy, right? S2 and S3. One thing will fit into S3, and you'll have 3 there going into S0. So what I'd recommend doing is maybe have a look. It's 2023 paper. Have a little look at that. I've printed it off so small, I'm struggling to actually see the values in there. I can see that one is 1 1 1, and I can see that one is 0 1 0. I think that one is, no, I can't see that one. Maybe 0 0 0 actually. Yeah, but yeah, please finish those off yourself. Right, it is important that a sequence generator is designed to avoid stuck states. Of course it is. We do not want stuck states, do we? Okay, so what are stuck states and why must they be avoided? So a stuck state is one that will never go back into the main sequence. Okay, and so it says, and why must the sequence generator avoid them? So if we start in a stuck state, it will never get back into the main sequence. Okay, so say what it is. It was a stuck state that you know, stuck state will not is a state that's not in the main sequence. On power up, if it starts in a stuck state, you will not get back into the main sequence. So that's why you should avoid them. Okay, only happens on startup. Once you actually started and it's happily going round, it will be okay. But this particular one does not have a stuck state actually. Okay, microcontroller is programmed to wait for a switch to be pressed and then light an LED for 3 seconds. It uses a switch unit which outputs a logic 1 when the switch signal was pressed. We're using the old 16F88 and we're using bit 7 on port A. All other bits are set as outputs. This is quite an annoying question because we normally say there's only 5 bits on port A, but there you go. They're using bit 7, but it should be okay. So how do we do it? Remember, we need to set up the tris A, to set up the data direction. So you're going to move, obviously bit 7 needs to be an input. Think of a 1 as an I for input, bit 7 is an input, all the rest are outputs. 6 5 4 3 2 1 0, and then we just quite literally move from working register to the file tris A. Now that's on the data sheet, guys, the tri-state A. That sets up the data direction. Yeah. Right, this is dead easy. Say what you see. It is literally that easy. So let's just read it. An LED connected to port A, bit 2, lights when it receives a logic 1. That's lovely. So we know that port A, bit 2 is going to be the LED. We know that. A delay subroutine called 1sec is available, and it creates a 1 second time delay. Well, hang on a sec. We want 3 seconds time delay. Let's move on. Okay, so first of all, make sure all outputs are logic 0. How do we make sure everything is a logic 0? How do we clear everything? Oh, I've said it. Clear file port A. Yep. Okay. So you probably could do, because I think there's only one, isn't there? Yeah, there's only one LED, isn't there? So I think you probably could do a bit clear file port A, comma 2 as well. You'd be okay with that. Anyway, is the switch pressed? Obviously, that's your checking bit test file. Skip if set. Port A, comma 7. Yeah. If it's not, then go back. So that's obviously go to begin. If it is pressed, lights the LED bit set file. Port A, comma 2. Call 1 second delay. Well, it wants to be 3 seconds, so literally do it 3 times. Do you know what? I'm going to write the word delay in there. I don't think you have to, but I will do anyway. Okay, and then obviously go back to the start again. So again, go to begin. This is quite an easy one. Whether it'll be this easy this time, because it's straightforward. Just so you know, if they're asking you about the interrupts, the int-con register, it's bit 7 and bit 4 need to be logic 1s for it to work. It even tells you that on the data sheet. So look on the data sheet, and it talks about those 2 bits. And then obviously, when you do an interrupt service routine, you need to protect the contents of the working register. So you normally do a move file or move working register to file temp1 or something, and then at the end you'd always move file temp1, comma W, which means move it back into the working register, and then you just ret-v return from interrupt enable. So that's the only slight difference with a normal subroutine and an interrupt subroutine. You just need to do those bits at the beginning. It's in the notes, it's on the knowledge organisers as well. Okay. Right, okay, so we're going to sketch a full wave rectifier. That's the one with the 4 diodes, so it's quite easy actually. It's basically 2 facing towards each other. So 2 faces towards each other, 2 facing away from each other. Oh, sorry, 2 facing away from each other, which is going to be that way. Okay, so we've got 2 facing towards, 2 facing away. It does say smoothed. So by smooth, you're going to have a capacitor in there as well before going into there. Now, I would probably get into the habit for this particular one of actually sticking, sorry, let's move that around to there, of actually putting it as an electrolytic capacitor. So stick a plus sign on there. Because non-electrolytics, the maximum capacitance you can have is about 1 microfarad. Usually a capacitor for full wave or half wave rectifier will be sort of maybe 100 to 1,000, something like that. So it'd be an electrolytic one. So it's just put a plus sign there. I don't think they'll take a mark off, but I'd still get in the habit of that. Let me just show you this, because students still, for some reason, still get confused with this. So the first half of the cycle, the first half, which is that bit of the cycle, the current is going to come that way. Obviously, it's going to go onto that plate, but it's going to go round like that. Obviously, because you have a load on the output, like some sort of resistance, it's going to go back and back round. Okay. So for your first half of the cycle, you'll be going through 2 diodes. You'll take 1.4 volts off. And for the reverse half of the cycle, let's use black. it'll be coming this way, and we're going that way again, also through this way, back, and then back out that way this time. So it will be flipping the signal up from the original signal. The original signal you have would be obviously 1.4 volts higher than that. We're going like that, yeah. So you can see the idea of it flips the signal up. That's how it rectifies it. What do we mean by good load? Right, line and load regulation. If we ask either, the idea is we want V out to remain constant. Even if the load current or output current, but I'll put load current, changes. I'll put fluctuates if you prefer. Fluctuates. That doesn't really look like the word fluctuates now, does it? Okay, so and load, sorry, line regulation is V out to remain constant, even if input voltage changes. So the input voltage there is called the line voltage, and the output current there is called load current. In both cases, we want the output voltage Vx to remain constant. Okay, that's what it means, yeah. So think about your mobile phone. When you unplug and plug in a mobile phone, you want the voltage to stay the same, but suddenly the current requirements change because you're plugging a load in. It's suddenly saying, give me tons of current. We don't want that voltage to change because it can harm and break the things that you're plugging it into. Okay. Okay, so how voltage followers work, which is the op-amp bit, is the two input voltages are kept the same. So if I know this voltage here, yeah, I'll call it X, it's got to be the same as the voltage there. Okay, so I can work out the voltage at X because I know that the output voltage is 15. So the voltage there, I won't call it Vx actually because I'll call it V1. So the voltage there I can work out V1 equals, we know how to do this, 30 over 60 times 15 equals 7.5 volts. Therefore, Vz has to equal 7.5 volts. And I think that's all you need to do. Let's just have a look at the equation. Yeah, that's it. There's your 3 marks. So as simple as that. Basically, the idea is these voltages have to be kept the same. Okay, that's how it works. Okay, so it's really easy. You could go a step further. Sometimes you could go a step further. You might be able to work out the current going down here, because obviously if you've got 7.5 volts there, you'll have 10.5 there. Yeah, etc., etc. Yeah. Okay. Okay, hopefully you got it on the previous page so you can still see the equation. But essentially, it's basically saying that the current out is 320 milliamps. So the current in is I1. That I1 is essentially IB. So it's essentially a very simple equation, isn't it? It's your HFE is IC over IB. Let's just write that down. We've been given IC. We need to find IB. So IB, so let's get rid of that. So IB, we'll call it I1 then. So I1 is the same as IB. Rearrange the equation, it's going to be IC, which is 320 milliamps divided by your 40, which is 8 milliamps. It is that simple. Yeah, it's just an IC over IB. Power dissipated, power is V times I. So we need to obviously find the I bit. Well, I said just previously, didn't I? You can find the current, because the current in that bit is Ohm's law, V over R, and the voltage was your 18 minus your 7.5, wasn't it? So it's your 10.5 volts over your 100 ohms resistor, which is 105 milliamps. Then we can work out the power. Power is VI. It's the power of the Zener. So it's your 7.5 volts, isn't it? Multiplied by your 0.105. I'll put that into amps. You can leave it in milliamps. It'll just come out in milliwatts. It's up to you. So from the data sheet, what have we got that as? So 0.787. Okay, right. To save me writing all of this, I'm going to try and explain the role of the non-inverting op-amp in this power supply when the output voltage starts to decrease. Okay, so when the output voltage starts decreasing, or if it does start to decrease, what will happen is the voltage, if you look at where it's fed, it feeds back into the inverting input, so that will start to decrease. Okay, then therefore remember the op-amp tries to keep the two input voltages the same. So if the voltage at the inverting input is decreased, then obviously what's going to happen is the op-amp output voltage will increase, and therefore it will suddenly push the output voltage back up again, because it will turn the transistor on more and it will just push it back up. Essentially, this process happens very, very quickly. You can't see it, so any slight fluctuations will do that. So that's why it's called a stabilizer. It's stabilizing the circuit, so it won't allow the voltage to drop, because the op-amp will turn on a bit more and it'll push it straight back up very quickly. So feel free to look at the mark scheme for that answer. I'm not going to write that one down. Hopefully my explanation helps, but obviously you can pop in and see me if you're unsure. Right, on this one, there's a few bullet points, so you need to sort of address them. So the specification says it runs off a 6-volt power supply. Well, I can see that's correct. So mention that spec is okay. An LED lights for 1 second if the light level is too low. Okay. So I'm going to check that this is 1 second. So time is 1.1 RC. 1.1 times 470 times 10 to the 3 times 2.2 times 10 to the minus 9. Get my calculator. 1.1 times 3 times 2.2 times 10 to the minus 9. Let me just press equals on that. Right, okay, so it's 1 millisecond, so I'm out by 1,000. 1.1 millisecond, 1.1 milliseconds. So any modifications, so basically if I'm out by 1,000th, I can make this 1,000 times bigger, or this 1,000 times 1.1 RC. Sorry, yeah, either of these 1,000 times less, but you can't really go less than 1K, so you're going to change the nanofarad. So change 2.2 nanofarads to a 2.2 microfarads capacitor. Yeah, that should solve that problem. The system is triggered by a push switch when light level is below 100. Notice we want to press for a logic 0, so will that give me a 0? It needs to drop below 1/3 of the supply to give me a logic 0. Where are we? So the the LDR is 10K. That's not quite 1/3 of the supply, so I don't think that will work. So I would say this system will not be triggered. So system not triggered as pin 2 doesn't drop to 1/3 of supply. Okay, so what you might want to do is you'd reduce the 4.2K resistor. So reduce 4.2K to something like a 1K resistor would be fine, wouldn't it? So something to give it a lower voltage, yeah. I can see straight away actually that pin 6 is connected wrong. Pin 6 and 7 should be connected together. So pin 6 should connect to pin 7. Okay. What's next? The LED passes a current of 10 milliamps. Does it do that? So 2 volts is dropped there. So 4 volts is there. Let's just work that one out. So I is 4 divide 390. 1, 2, 3 gives me 10 milliamps, so that is absolutely fine. You could put a calculation there and say that is fine. So basically I just did I equals 4 over 390. Yeah, that's what I just did there. Yeah, I said pin 2. Yeah, we said about that one. 555 is 6 volts. Yeah, that's okay. So there we go. So your 3 suggestions were to change pin 6, to change this resistor here, obviously change that there, and obviously to say that this bit is okay. This bit does meet the spec. So as long as you sort of said all of those and sort of spoken about them, then that is fine. So you've really evaluated that circuit there. Okay. Okay, this one, remember if the capacitor and resistor are in series, it will be a charging capacitor, a charging type circuit. This one's dead easy actually, because you've got 12 volt supply and it's asking for 6, so it's not on a data sheet, but hopefully you remember the time it takes is 0.69 RC. So 0.69 multiplied by 43 times 10 to the 3 multiplied by 68 times 10 to the minus 6. Let me just check on the data sheet, on the mark scheme, 2.02 seconds. Now, you can use the equation on the data sheet if you really want. It will be the charging one, and it will be the time one, with the minus RC ln VO over VC. Was it VC over VO? It's the yeah, VC over VO, I think. Yeah, that way around. Yeah, it's on the data sheet anyway, so you could use that equation if you wanted to. Okay, but I would probably stick with obviously the 0.69 RC one. So I'll take that one off. So you've already got that there. Right. Calculate the frequency and time period. So on the data sheet, you get this equation. It is F equals 1 over RC. That is related to the Schmidt A-stable. Okay, so that will tell you the frequency, and then obviously time period. We know what time period is, 1 over F. So let's work this out. So 1 over 43 times 10 to the 3 times 68 times 10 to the minus 6 equals 0.34 hertz. And then time period 1 over 0.34 gives me 2.9. Okay. Okay, this year they've not asked you to do anything with the Schmidt inverter. They've basically just said what is the voltage across the capacitor when the output voltage it goes from 12 to 0. Remember, it goes as far as it can go and then down. So the answer is 6 volts. And then when it comes back, it goes as far as it can go back and then back up. So the decreasing switching threshold would be 4 volts. The increasing switching threshold would be 6 volts. Sometimes they might give you some sort of weird kind of wave like that, and then you would have to go across at 4 and 6, and then you would have to go like up, down, and so on like that when it goes past these trigger points. Yeah, so sometimes it will ask you to do that. This time it's basically just saying Complete the graph to show the behavior of the output of the astable over a period of 10 seconds. So it's part of the same question from before. So I know that the time period is 2.9 seconds. So it's going to be on for half of that. So I'm going to go for 1.5 off or 1.5 on. It's 12 volts, isn't it? 1.5 off. Oh, so yeah, I'm going to go to 3 because I'm going to make it easier for myself. Yeah, I'm rounding it to 3. You're going to 12 volts, obviously, because it says the output needs to go to 12. Try not to get scared with these questions. They're actually all right. Yeah, they're not too bad. Okay, so that is all that one is saying. Okay. Okay, so design a subsystem to divide it by 4, and we're going to create an up counter because it doesn't tell us to do a down counter, does it? So we might as well do it as an up counter. So Schmidt astable goes in there. Divide by 4. Well, one D-type flip-flop is called a divide by 2 counter. Do you remember that? So if you literally put a D-type flip-flop in there, you will divide by 2. So D clock, Q, not Q. How do you design one of these? So easy. D loops round to not Q, doesn't it? Think about it, guys. If D linked round to Q and whatever's at D goes through to Q on the rising edge, you'd never flip. It would always stay at a 1 or always a 0. So just think about it logically, guys. Yeah. So that's that one. There's your output. If you want an output, you can have it as an output. And then the next one is here. And then obviously this is dividing it by 2 again. So I've divided by 2, and I'm dividing it by 2 yet again, because that feedback thing divides by 2. I'm drawing it as an up counter, which means that not Q goes into there. And then there is my output. So that has divided by 2, divided by 2. Okay, sketched as up counters. I think if you did it as down counters, I don't think it would matter. So we have missing boxes. So obviously preamps always go into your mixer, don't they? Summing amp or a mixer. Sorry, let's get my pen. They go into my mixer. Then we normally have some sort of tone control, filters. Yeah, I'm going to call it tone control. I think it'd be okay calling it filters. And then Z is obviously it's obviously got to be a power amp always before the loudspeaker. It'll always be a power amp, won't it? Okay. What is a function of decoupling? Basically, they will only allow AC through. They will block DC. So block DC signals. Okay. What is the advantage of an active over a passive? Gains of more than 1, of course. Yeah, that'll do. And that's it for that bit. That's easy. Okay, from the previous page, it was a bass cut filter, by the way. So it was one of those jobbies. Easy, isn't it? If it's in series, it's a bass type filter. So bass cut is that one. If you put it in series with the feedback, it's a bass boost. And then it's the opposite for the treble. So you put the treble in parallel with the feedback. It's a treble cut. You put a capacitor in parallel with the input resistor. It will be a treble boost. Okay, but try and just learn them. That should be okay. Right, voltage gain from the previous page. Gain is minus RF over RN. It was 750 over 15, which equals minus 50 because it's a negative there. And then the breakpoint is with the resistor in question, so it's the input resistor. So 1 over 2 pi times 15 times 10 to the 3 times the capacitor value, which was, looks on this to be 68, times 10 to the minus 9, which looks to be 156. And then it's a base cut. The gain is 50, so the gain is 50, 156. Remember, there's 100 there, that's 200 there, so 150 is about 3/4 of the way along, so it's about there-ish. And it's a base cut, so 45 degrees, straight line. There we go. Okay. I can't believe they give you 5 marks for that, but they do. There you go. Okay, so from the previous page, perhaps I should have brought this this one over, so I do apologise. From the previous page, you had a shape like that. If you have 300 Hertz, you're around here, the gain would still be 50. So for the 300 Hertz, also 300 Hertz, V in times gain equals V out, so 75 millivolts times your 50 should equal 3.75 volts. Okay, if it's a frequency of 100 Hertz though, 100 Hertz, you might be about here-ish. I'm just going to go from the mark scheme, but obviously feel free to plot it yourself and have a little look at that. The mark scheme says the answer is 2.4 volts, so 2.4 divided by 0.075. So yeah, so the mark scheme saying it's about 32-ish. So the gain is about 32. I'll put about. Oh. So saying the gain is approximately 32. So V out equals 32 times 75 millivolts. Okay, so 2.4. Notice, obviously, the frequency doesn't change. It's not quite sure why they give you that box to write that, but there you go. You're not manipulating the frequency, are you? You're only changing. Filters don't manipulate frequency. You can change the frequency, but it's only the voltages that change. They cut high frequencies and cut low frequencies, but the frequencies themselves aren't changing, are they? Okay, so we have the PCM transmitter, the PCM receiver. Let's just quickly jot down these. You should know all these anyway. Quite easy, isn't it? ADC, piezo, shift, register. Write register if you want. I'm just going to write reg. And the CPO. Reg, and then obviously your DAC. Okay, so the maximum audio, so if you've got 10K, then the maximum audio will be half of that. So half of the max sample frequency, yeah. So basically, it's called Nyquist. Okay. I'm not going to write these next two down, I'll just explain them. So the function of the following blocks: the Schmidt trigger regenerates the signal. It removes noise distortion, okay? So it can remove noise and distortion. The low pass filter removes any unwanted frequencies caused by quantization. So you get something called aliasing. And basically what happens is if you don't sample at least twice the highest audio, you don't get a true representation of the signal. So you've got to cut off every frequency, in this case above 5 kilohertz. If you're sampling at 10K, you cannot have any more frequencies above 5K. So you need to chop everything off. So the low pass cuts off all the unwanted frequencies, okay? Right, here we go. The name of this modulation use is obviously PAM, because the amplitude is changing. On the block diagram of the PCM system above, add an arrow labelled X to show where this system is found. So if we add an X where this is found on this system, so where are we looking at PCM? The pulse amplitude, it's this bit, it's the sample gate bit here. Yeah, so that's where it's found. Okay, so that's that one there. And then distinguish between frequency division multiplexing and time division multiplexing. So again, instead of me just writing all this down, where are we? I can probably tell you that. Is it on here? Where are we? Yeah, so frequency division multiplexing allocates a different carrier frequency to each signal. The signal is modulated onto the carrier and transmits continuously. Okay, so that's what frequency division multiplexing is. In fact, we usually use frequency division multiplexing with AM and FM, because obviously if you've got the FM band, how many stations can fit on that band? It's called frequency division multiplexing. So like radio 1, radio 2, etc., etc. So you can work out how many would fit on that band. TDM, basically, again, I'll read from the mark scheme. In TDM, each signal source uses the full frequency bandwidth of the comms link, but only for a short time. Then a different source transmits in the same way for a limited time. In other words, the signal sources take turns to transmit down the link. It does say equivalent answers, so I would probably say that you've got a bit of time in between when one sample comes in and the next sample comes in, so you can get more than one signal down the same transmission medium. So something along those lines. So using the last bit, using the information in the block diagram, how many PCM channels identical to that above can be combined onto the TDM link. So basically, I'm going to write this answer in here. So I'm going to write this answer here, just so you can see. So what I'm going to do is I'm going to work out the time period of the sample gate. 1 over 10k is 0.1 millisecond, or 100 microseconds. Okay. Then I'm going to work out the time period of the clock, but then there's obviously 10 bits. So 1 divided by 2 meg is 0.5 microseconds for 1 bit. But it needs to get all 10 bits out, doesn't it? So this clock here needs to shift all 10 bits. So 5 microseconds for 10 bits. So essentially what we've now got is we've got a sample coming here, a sample coming here. This sample lasts for 5 microseconds. This sample lasts for 5 microseconds. But there's all of this time in the middle, in between, because that's 100 microseconds long. Yeah, so there's 100 microseconds length there before the next sample comes in. So how many will fit in? It's literally going to be 100 divided by 5 equals 20 channels. Hope that makes sense, yeah? So I basically just converted that into a time period, that into a time period, times it by 10 because it's 10 bits, and then just work out how many fit in. So it is that easy. So you can get you get 4 channels there. Yeah, 4 channels will go down that comms link. Okay. Okay, so this one is a fibre optic one. So one cause of attenuation. Okay, so what do we mean by that? Basically, impurities in the glass can do this. So you could or scattering and things like that. But yeah, impurities in the glass will attenuate the signal. It basically means that the light won't get down very far. So impurities is the main thing. Impurities in the glass, because it's not, it's not perfect. Dispersion. What do we mean by dispersion? Well, light, unless it's purely one frequency, if you've got more than one frequency going down, then they will take different lengths. Different frequencies will take different lengths. different paths, should I say, not lengths, different paths. So when you get this frequency at the end, the pulse may be a bit not as sharp, yeah. So it disperses. So basically, it's basically saying that something like a light pulse contains different frequencies. Something like that. So each reflect at a different angle. Different angle. Yeah, so that's the idea. Right, this one here, let's have a look. This is basically your classic, you know, your gain one again. So it's the gain in decibels equals, or overall attenuation, should I say, equals 10 log of P out over P in. So basically put the numbers in, 10 log, it's always log to base 10 anyway, P out is your 5, isn't it? Because yeah, the output is 5, yeah. So 5 microwatts over 100 microwatts. The micros will actually cancel. That's going to give you 13 dB. Okay. So that's your answer for that. But then it wants to calculate the loss per kilometre. So it's 40 kilometres long. Then we just go 13 dB divided by 40 km will equal 0.33 dB per kilometre. So every 1 kilometre you're losing 1/3 of a decibel. That's basically what it's saying. Okay. Okay, so this is it's asking us to draw the piezo parallel in, serial out, and it's asking us to draw a 3-bit one. So it's going to have 3 of these D types. So 3 D types, QC, QB, D, D. There's the S's there, and then your clocks there. Obviously connect the clocks together, that's the easiest thing. So let's do that. Okay. So that's that one. It's a shift register, so that goes into there, that goes into there, and that's obviously your output there. And then the parallel input with the load, so we need to obviously move it in, so we need to load it in. So you can't just feed them directly in, you need the load. So what logic gate will connect this with this? If you sort of say it in your head, hopefully you can get the idea that you need 3 AND gates there. So it's quite a tricky one. So you've got your 3 AND gates there, so the load will go in to all 3. Like that. We'll use a different colour for the next bit. And then these can sort of move over. That one there. That one there. That one there. Okay. So that is 6 marks for that one. Please do it neater than me. Okay. Decoder uses a photodiode. If you remember a photodiode, we use in the reverse bias mode. That's how they work. So you actually because you want to put energy onto it, so you actually put it in the reverse bias mode. So actually use a photodiode in part B in the reverse bias mode. Okay. So they're the photodiodes. Normal LEDs are in forward bias, photodiodes with reverse bias, because you're almost doing the opposite essentially. You're putting light onto it. Yep. Thyristor. So complete the circuit by adding a switch and another component. Okay, so it always starts from here, doesn't it? I'll just get a pen. So we need a switch, and what's the other component we always put for the switch? Okay, so that's that one. When the lamp is off and S2 is open, what are the voltages X and Y? So the lamp is off, S2 is open. So if the lamp is off, all the voltage is across the thyristor, so it's going to be 12 volts. And then obviously the voltage at Y would also be 12 volts because it'll be like an infinite, S2's, if it's open, it will have an infinite resistance. When the lamp is lit, which means it's on, S2 is open, what are the voltages? So when the lamp is lit, that will obviously be 0 volts. That will still be 12 volts. When the lamp is lit, pressing S2 for a moment turns it off. Explain how this works. So again, I'll go into a math scheme so I can get it exactly right, what they say. So when S2 is closed, the voltage at Y drops from 12 to 0. So when S2 is closed, the voltage at Y drops from 12 volts to 0 volts. I'm sure it's going to say the voltage at X. Yep. The voltage at X drops, or must drop, by the same amount. It drops from 0 volts to minus 12 volts. This will turn the thyristor off. That should do. Okay, next one. Two components. Well, that's your bog standard capacitor and resistor, isn't it? RC network, yeah. Can't believe that's it. Is that it? Yeah, I think it is. Oh, no, allow the brightness to be varied. There we go. Make it a variable resistor. That can be varied. Right, okay, we have the classic diac and triac. Okay, if you remember that V1 and V2 should add up to the dotted line. So V1 is always the voltage across the triac. V2 will be the other bit, which will add up. So you can see it'll all be that bit there. It will be that bit there. It will be that bit there. You can see the idea. It will be that bit there. So it will add up all of this bit here. You don't have to colour this in. I'm just kind of showing you the bits that would add up. When would it be at full brightness? At this point here. Yeah, that's when it will be at full brightness, because that's when I have the highest potential difference across it. Okay. I hope that makes sense. Anything else you can get asked about these? Just remember the diac as well. It can ask about why would you have the diac. A couple of things. It will improve the rise time of the circuit. So essentially, that's what you want to do. It will also ensure the triac dissipates less power, because the triac will gradually turn on, much like a transistor. But if you have a diac there, as soon as you get the 30 volts across a diac, the triac will instantaneously turn on, so it will consume less power. So there's a couple of reasons why you'd have a diac there.